While walking, people can naturally handle interactions with other pedestrians and obstacles. Inspired by this phenomenon, we propose HEIT, a reinforcement learning network for robot navigation in crowded and constrained environments. HEIT encourages the robot to reason about different spatial and temporal interactions among humans, obstacles, and itself, improving the robot's safety and efficiency. First, before learning a policy, we need to come up with an input representation of the crowded and constrained scenario. Previous works use group of circles or point clouds to represent everything. In this simulation scenario, the robot is overly conservative and deviates away from the optimal path. Eventually, the robot fails because it does not understand that humans only block its path temporarily, while obstacles are permanent. For the same reason, Ross' navigation stack causes the robot to spin and eventually get stuck in a narrow corridor. For height, we split the human and obstacle representations so that the robot policy network can easily distinguish the dynamic and static obstacles. As a result, the robot has learned different collision avoidance strategies for humans and obstacles, and therefore succeeds in the same episode. Then, let's move on to network architecture. Spatial temporal graph, or SD graph, is a principled way to model multi-agent interactions through space and time. A common practice is to formulate the scene as a homogeneous graph with uniform nodes and edges, and then use a single attention network to learn the robot policy. When the robot encounters a denser crowd during testing, without distinguishing the interactions with humans and obstacles, the robot did not keep a larger distance from humans, which results in collision with one of the humans. In contrast, we propose a heterogeneous SD graph, where different edges represent different types of interactions. Using a different module for each type of edge, we derive the height network architecture. Height is decompositional in nature, yet end-to-end trainable. In this way, we design a network architecture in a structured manner without adding additional training steps. In the same testing episode, height encourages the robot to avoid the most crowded region yield to humans for safety, and navigate along the obstacles for efficiency.